Is that fine? Thank you. Cool. All right, we are recording now. So welcome to the FFT review session. I'm going to talk briefly about FFT, what it is, how it happens, and then we're going to do 2 FFT midterm questions. They're kind of similar, so if we only get to 1, that's fine. We'll have time for questions at the end as well. And to be honest, that is probably more important than getting to both midterm questions. So FFT, fast Fourier transform, is an algorithm for doing the discrete Fourier transform, the DFT. In this class, we phrase it as you have a polynomial and you want to evaluate that polynomial at, the polynomial has n coefficients, and you want to evaluate that polynomial at n different points. Because maybe you want to multiply 2 polynomials together, that is n squared time if you have coefficients, but it's only n time if you have values. So the FFT consists of noticing that there are a lot of really nice properties about the complex roots of 1, the nth root of 1, a root of unity. I'm going to share my screen here and show you what that looks like. So here we are. This is the matrix multiplication view of the discrete Fourier transform. This thing here is called the DFT matrix. And when you multiply it by this vector of coefficients here, you take the vector, you turn it on its side, you do the dot product of every row, you will see that you have evaluated that polynomial at all of the nth roots of unity. You can convince yourself that this actually works, but that shouldn't be too big a deal to do. So I'm not going to go through exactly why that's the case just yet. Just notice that here we've said A0 is the 0th coefficient, A1 is the first, A2 is the second, etc. And so we would want to do, say, if we're evaluating this polynomial at omega, which is what we call the first nth root of unity, or the smallest nth root of unity. Omega to the 0 is 1, omega to the 1 is omega, omega squared, omega cubed, and so on. Now, when you have the nth roots of unity, and there's a bunch of other stuff here, you can ignore it. I'm going through the note that I wrote about the difference between polynomial, the Fourier transform in the polynomial view, and the Fourier transform in the signals and frequencies view. But I'm just sort of co-opting the nice pictures that I drew here. This is a picture if we put all of the roots of unity on the complex plane, where the x-axis is the real part and the y-axis is the imaginary part. This sequence here is a view of what all of the roots of unity are. In this case, it's the 8th roots of unity. Sorry, was that a question? No, okay. Do feel free to interrupt if you do have a question. So this, as you can see, here's 1, because it has 1 on the real axis and nothing on the imaginary axis. Here's -1, here's I, here's -I. Any of these things, if you raise them to the power 8, you will get 1. That's what the 8th roots of unity mean. They're just the things when you raise them to the 8th power, you get 1. I've drawn them with these little circle around them as it is, because they rest on the unit circle in the complex plane. Now, here is the fun thing. Oh boy, Zoom bugs, that's what's fun. Oh boy, this is going to be an issue. Yeah, no, that's not going to work. Okay. I was going to annotate this, but Zoom is not going to let me do that. So instead, I am merely going to, can you see my cursor here?
Yes.
And can you see the big thing that I'm dragging around with it?
Yes.
Yes.
Okay, cool. Awesome. As you can, I am not holding left click right now. Zoom is bugging. So I was hoping that you could see the cursor and not the not anything else. But anyway, so if you look at this sequence of oh boy, if you look at this sequence of roots of unity, what you might notice, there are a couple of things you might want to notice. First, that in fact, if you take a root of unity and raise one of these roots of unity and raise it to the second power, for instance, you get a different one of these roots of unity, right? If you take -1 and you square it, you get 1. Fine. However, if you take the first root of unity, which is this one here, which is a 45-degree angle, or what's that, pi over 4, away from the x-axis, and you raise that to the second power, what you get is something, you get this sort of third root of unity, or sorry, the second eighth root of unity here. When you take basically two numbers in the complex plane that are on the unit circle and you multiply them together, their angles away from 1 add. So you can derive that from Euler's formula. And here, down here, I've written everything is to the power of 3, and I've written what that looks like. So here, 1 is just, there's a 0 in here, so we don't care. Here, there's a 3, so it's 3 rotations away from 1. 6 is 6 rotations away from 1. 9 rotations away from 1, which is the same thing as 1 rotation away, because we're working mod 8 here with the 8th roots of unity. So you can draw this very nice correspondence between what the root of unity looks like on the complex plane and what it actually is in the e to the I theta view. So this is how you can visualize the roots of unity. What I want to say is take a look at every other root of unity here. The 0th and the 2nd and the 4th and the 6th, right? What are those? If you look at just that sequence, you get 1, I, -1, -I. Somebody tell me what those are?
I think those are the 4th roots of unity.
Those are the 4th roots of unity. Yes, thank you. So that's where FFT comes from. When you take all of the nth roots of unity and you split them between the even numbered ones and the odd numbered ones, you get, on the one hand, just the n over 2th roots of unity, and on the other hand, 1, 3, 5, 8, or 1, 3, 5, 7, sorry. You get also the 4th roots of unity, but all of them shifted or rotated a little bit, which is to say all of them multiplied by this thing here, the first 8th root of unity. Does this make sense to people that you can decompose the roots of unity into the n over 2th roots of unity just with some modification on one of them? Cool. Now, what you can notice is that um,
Yeah.
when we go to further roots of unity, here, let's say that we're working with omega squared, and that's the point at which we want to evaluate our polynomial. Now we evaluated it. We take a0 times 1. We take a1 times omega squared. We take a2 times omega to the 4th, and so on, which is, you can see what this is. We get these numbers out. If we go all the way to the end and we say that we're working with omega to the n minus 1, as that's the last thing we need to evaluate our polynomial at, omega to the n minus 1 is actually the same thing as omega to the minus 1. You can convince yourself of that. You can convince yourself of that just using the geometric view or using Euler's formula. And what that means is that in a way, it's exactly the same thing, but with just a minus sign put in front of it, or a minus sign in front of the imaginary part. So if we take this matrix multiplication, which is the evaluation of our polynomial that we want to do, and we split it into the even and odd columns, we will get this this notion that we have just the n over 2th roots of unity, and some of them are going forward, some of them are negative and they're going backward, and we can do all of this just by doing evaluating something at the n over 2th roots of unity a couple of times. That is basically just the high-level view, which covers all of the salient points. If you want to understand FFT very in depth, that's probably not enough, but hopefully you can look at the book. The book explains it very well, and it'll make a lot more sense now that you've seen this way of looking at it, because I'm not sure that this is something that the book does, or at least not well. Any questions about this view of FFT, what it is and how it happens?
Why do you have that criterion for choosing the omega?
We choose omega basically specifically so that we can do this. If we wanted to just evaluate our polynomial so that we could multiply two polynomials together, we could do it at any n points. It would work. Any n points, it would be fine. But we don't want to do it at just any n points, because some of them you can't do better than n squared. Here we have noticed, or really, Cooley and Tukey and the people who were working on this for frequency reasons, noticed that there's this very nice way of splitting it into even and odd, and that when you do that and you do the whole divide and conquer recursive thing, it only takes n log n time instead of n squared time. That's why we choose omega, omega squared, omega cubed, etc., all the way to omega to the n minus 1. That's why we choose the roots of unity to evaluate our polynomial at. Other questions?
During FFT, why do we choose a primitive root of unity?
You're saying, why do we choose a primitive root of unity, as in this one?
Why do we choose a root of unity that doesn't appear on the levels below it of recursion?
Oh, one that doesn't appear on the levels below it.
Yeah.
So when we recurse from the 8th roots of unity, let's say, we're going to go to the 4th roots of unity. We need this one. If we take our first coefficient, not our 0th coefficient, but our first coefficient, our 3rd coefficient, our 5th coefficient, and our 7th coefficient, and we evaluate it at the 4th roots of unity, we won't actually have multiplied it by these 4 numbers here. we'll have multiplied it by these four numbers, or multiplied it and then added together. You know what I'm saying? And so in order to turn it, basically, so that we are actually evaluating it at 8th roots of unity, when we really did the FFT to evaluate it at 4th roots of unity, we need to multiply by, oh boy, we need to multiply by this primitive factor, basically. This factor here that appears in all of them, that rotates from the 4th roots of unity to the odd bits of the 8th roots of unity that we actually want. Other questions about this? It's good to understand more or less why this works. All right, now, question is, why is this useful? Why do we do this? Well, for one thing, it's good to be able to evaluate polynomials. It's good to be able to find frequency components of signals. These are actually exactly the same thing. You can look at this note, which I posted on Piazza, if you want to see the correspondence there. But we want to multiply polynomials together, say. And so we want to evaluate the polynomial, or evaluate two different polynomials, multiply them together element-wise, rather than coefficient-wise, and then go back to the coefficient representation. If you do that, you will only take n log n time, because because you're only doing FFT a couple of times, and then the multiplying it in the values space is just an element-wide multiplication, and it's only linear time. In order to do that, how do what kind of an FFT do you actually do? Well, you need to choose some roots of unity to evaluate your polynomials at. And you need to choose roots of unity so that you have enough of them that you can actually represent the polynomial that you're going to end up with. Remember, a degree n polynomial can only be, is this right? A degree n polynomial can only be represented uniquely by n plus 1 different points and its evaluation at those points. So if we have something that goes up to the 8th, we have to evaluate it at the 8th, or something that goes up to the 7th, rather. We have to evaluate it at the 8th roots of unity, or else we're going to get confused. If we think, if we're multiplying two degree 2 polynomials together, say, each of them, we would have to have at least 3 points at which we evaluate them in order to represent them uniquely, in order to represent them faithfully in the value space. But we're going to multiply them together, and the next one is going to go up to the 4th. So really, we need 5 roots of unity, at least, in order to represent the resultant once we multiply them together. So what we do is we take the power of 2, which is the smallest power of 2, which is large enough for our purposes. If we know we need 5 points, we take the 8th roots of unity, and that'll give us 8 points. The reason we do a power of 2 is because we're doing this divide and conquer thing here, which divides the size of the problem by 2 every time, and we don't want to end up with an odd-sized problem at any point, because that would be more complicated, basically. There are ways to deal with that. I believe the review discussion sheet from this week, which has just a bunch of review problems on it. One of them is an FFT review problem, and it talks about one of the ways to deal with that. And it's useful to see that and think about it. But when we're doing the standard FFT, we choose a power of 2 for that reason. Questions about choosing a power of 2 that's big enough so that you can represent your polynomials, multiply them together, and still get the right answer on what kind of a polynomial you've gotten out of it. Cool. So we have this method now for multiplying polynomials together. Normally, if you wanted to multiply polynomials together, you would have to take, if you wanted the fifth coefficient, you would have to take a0 times b5 plus a1 times b4 plus a2 times b3 plus a3 times b2 and so on. You would have to do that whole thing, that whole sort of dot product. And to do that for all of the coefficients would take n squared time. Instead, you can just make sure that you have enough roots of unity, do the FFT on both your polynomials, multiply them together in the Fourier space. You're multiplying them element-wise, so it's quick, and then do the inverse FFT. The inverse FFT, it's a little bit hard to understand, at least for me, why it works. But one way to understand it is that you just need to multiply by the inverse of this matrix. And it is pretty, if you like the linear algebraic way of looking at it, if you just invert all these things, you'll get the inverse matrix. That's because these are all complex numbers with absolute value 1, and the matrix is symmetric. You can convince yourself however you like through whatever math, whatever algebra, that just doing the FFT where you pick the roots of unity in inverse order, so you start with omega to the -1, that will get you back into the coefficient space. But that is what happens. And in fact, you have to multiply by 1 over n when you do that. That should make at least some sense. Here we have multiplied by for example, in the top row, we've just added all the coefficients together. If we were to take all of our results in the value space and add them together again, we would essentially have multiplied by n in that case. This matrix is not, when you invert this matrix, you don't get something very similar. This matrix is not quite unitary. It's actually like square root of n times a unitary matrix. So you do have to multiply by 1 over n when you do the inverse FFT, because you've introduced this sort of multiplicative factor by doing the FFT in the way that we do. Questions about that? Okay, cool. So I'm going to stop sharing if I can, which is dubious. Oh boy. This is bad. Why is this happening? So while I try to figure out how to stop sharing, look at fall 2019 midterm 1 and look at, I believe it's question 5. Tutors, readers, correct me if I'm wrong there, and post a link to that in the chat. The link to just the exam, not the solutions. Look at the solutions later. I believe we got it from the TBP website, something like that. Sound good? So everybody just look at that. It'll ask you basically to create polynomials to do some other problem so that we can use FFT to do it quicker than n squared. The idea is to find the structure of polynomial multiplication in a different problem. All right, go do that for a bit. Since it's probably best to do it on your own, since it is an exam problem, I'm not going to open breakout rooms. let's just do that for a bit. Maybe I'll open breakout rooms for the next one. And again, just unmute yourself if you have any questions while I am trying to stop sharing here in the presence of. Thank you for restarting the recording. I am going to start talking about the solution. So you can just, if you are still working, you can just, turn off your sound on your computer and watch this later if you like. This is going to be posted. What this is called a convolution. All of the things where we would use FFT to sort of get the structure of polynomial multiplication, where you have to do all of these dot products and put it into something else, that's convolution. You can look up convolution. It's useful to see that what we're doing in here in particular is called the discrete time convolution, because we're not working with continuous functions. We're just working with, there are only a few coefficients in our polynomial. What you should think about is, where does that sort of idea, where does that appear? Where does the idea from polynomial multiplication appear? What I'm going to do is I'm going to do this. Hopefully I have the answers here. Yeah. So I'm going to start sharing, and we're going to look at the solutions. So the first two parts of this question, we're asking you just to recognize the structure of the polynomial multiplication itself, which is very, very useful. Let's see here. No bugs, no bugs. Share. Cool. Works. So you can see the first one, we're looking for the coefficient of x squared, right? A0b2 plus A1b1 plus A2b0. That makes sense. The next part asks you to generalize it. And essentially, it points out that you take all of the coefficients, all of the pairs of coefficients where the exponents add up to k in order to get the coefficient on x to the k. This here should actually be times, not plus. But you can see ai x to the, and this should be ai x to the I plus bk minus I x to the k minus I, or times rather, is ai bk minus I x to the k. This should also make sense to people. And what that means now is that when we do multiply these things together, we get this summation of products thing. This is what happens. This is a dot product, and this is what happens in a convolution. Somebody else had a different name for it. It was like a, what did you call it? Was it Max? You had a different name for it? Repeated dot product, something like that.
Yeah, like successive dot product. Successive
dot products. Yeah, that's a good name for it, because that's what you're doing. You're taking A and B and you're taking the dot product. You're sort of sliding them past each other and taking the dot product at every point. In one of your homework questions, this was used where one of the polynomials was much smaller than the other. And so you were sort of comparing it to the other one. I believe that was the DNA comparison thing. And in this one, what you can see is that we have, let's see, AI bk minus I. We have these elements of this dot product go into these dot products, in this case where the two polynomials are the same size, you're still sliding them past each other. It's less of a measure of similarity, because in a lot of cases, you're going to be comparing like only half of one polynomial to only half of the other, but it's the same basic idea. It's still the same convolution. And in fact, what you can notice is that it's doing that when you've flipped one of them around. You've taken one of them and you've put it backwards and you're doing this dot product between them. Because AI times BK minus I, and then AI plus 1 times BK minus I minus 1, and so on. So now it asks you to apply it. And it asks you to note that if you have probabilities, what's the probability that A plus B is going to be K? Well, these are discrete variables, so it's pretty easy. It's that A is 0 and B is K, or A is 1 and B is K minus 1, or A is 2 and B is K minus 2, or whatever, and so on. So this actually gets exactly the structure of polynomial multiplication. This is just kind of a fact that when you add two random variables together, the probability distribution of their sum is the convolution of the distributions of the two variables that you added together. So really, you just create a polynomial, which is all of the probabilities in the one random variable, and another polynomial, which is all the probabilities in the other polynomial, and you do FFT on both. You multiply them in the Fourier space, and then you do inverse FFT. Now the question is, let's say that n is 5. Why not? N is 5. What roots of unity do we use? What you might say is 8. We might use the 8th roots of unity, because FFT needs power of 2 roots of unity, and that's the smallest power of 2 less than 8. But actually, we would have to use 16, because we have n minus 1 is the largest value that A or B can take on, right? Let's say that's 4 in our case, when n is 5. Each of them can take on 4, 0 through 4, but in fact the sum could take on 0 through 8. I mentioned this earlier. When you do a multiplication, when you're doing a multiplication of polynomials, you have to be able to represent the sort of resultant polynomial, and you have to have enough roots of unity to do that. So if we had 8 is the maximum that our 8 is the maximum value that our new sum random variable could take on. We have 9 total values. The smallest root of unity greater than that is 16. The smallest power of 2 greater than that is 16, rather. And so we have the 16th roots of unity. Now, that's still n log n, because even if you double something, and then maybe you have to as much as double it again in order to get it to a power of 2, whatever, multiply by 4. N log n times 4, if you multiply n by 4, it's still O of n log n. There's just a 4 and maybe something else out in front. It's not that big a deal. It's still a constant factor, so it's still O of n log n. Questions about this? This is very much a textbook application of FFT, because it is just straight convolution. In other questions, you might have to be a little bit more clever about it. You might have to look at, oh, here's this nice sum of products that I can get. Can I use it elsewhere? Maybe you have to turn one of them around because you're going to compare two strings more directly. Maybe you have to multiply together two polynomials, and the resultant is going to be full of garbage, except there are going to be a couple of things which are useful. So that is the idea, that you just look for that thing right there, the sum of products. You're going to compute a bunch of sums of products at once when you do FFT. Look for that in your problem, see where you can find it. Any questions about this problem or problems very like this?
Sorry, have you started part 3 yet?
Okay. If you have do you have a question about it, or?
Yeah. So for part 3, why wouldn't you? So the algorithm that they show is n log n, but you can just do it in k time, because you're just doing k multiplications and then k minus 1 additions, right? So what?
You want to
Yeah, what's
compute
the
it
point
for
of
all
that?
relevant k.
Yeah, and you have k multiplications of I equals 0 to k, and then you're
However-
adding those together.
However, we want to compute it for all k at once. We're not given a k that we want to compute it for. We want to compute it for all k at once. And so
So for all k 0 to n minus
Yeah.
1.
and in
Okay,
particular,
that makes sense.
you know, if k could be as large as n, or even as large as 2n, because a could variable a could be n minus 1 and variable b could be n minus 1. You know, n times k is still n squared. So the Fourier transform would still be a good idea. It's only if k is very small that it's faster.
Okay, thank you.
All right. Any other questions about this?
Hi, for this question,
Mhm.
would it be the same thing if we reversed one of the coefficients, like one of the polynomials?
I think not, because I think then you would be getting the probability, you know, instead of getting the probability that a plus b equals k, I think it would be like the probability of a plus n minus b, or n minus 1 minus b equals k. I think it does matter that they're in that order, because you do want to multiply the probability that a is 0 by the probability that b is k, and not the probability that b is n minus k. Other questions about this? Cool. What time is it? I think we are out of time. I'm going to stop sharing. If you have more questions, feel free to ask them. The chat has been popping off apparently. But yeah.
Sorry, I do have a question kind of related to this stuff, and I asked in the chat, and I think somebody responded, but I'll just confirm with you too. So, like the protein matching question and like homework 5, question 5, like they're both kind of determining like which coefficients or like which degree term we should start looking at, but I'm a little bit confused about how you determine that, because like, or how you would prove it rigorously, because like I get like that you would notice a pattern when looking at a bunch of examples or something like that, but I guess I don't really know how you would prove it rigorously, or like even if how you'd find it if you don't have the time to do a zillion examples.
So if you are able, so basically you would look at it analytically. This formula for polynomial multiplication, where it's ai times b k minus I, and then you know sum over all I,
right,
is generally true. That's not by generally true I mean true in general. It's always true. It's not, that's not a fact of how you do the multiplication. It's not a fact of what polynomials those are. That's just a true statement, and you can prove it if you need to. So what you would do is you would say that, well, look at these polynomials that I have. When I multiply them, the kth coefficient of them is going to be this. And so I can extract whatever information I need from that.
okay.
Hopefully that makes sense, that you use basically the way you would express the resultant polynomial if you weren't using FFT to multiply them, and you use that in order to make a statement about what information is going to be there.
Like when you're not using FFT, like you can see like the expanded version, like in the protein matching question, for example, you need to have like n terms of a certain degree in order for it to be a valid like comparison. Otherwise, it's not.
Yeah.
But like how, I guess, still
But
like
the thing is, FFT computes the exact same
Yeah.
multiplication. So
Well-
it is still that thing.
Mhm.
If you write out this expression for what the kth coefficient of the resultant polynomial is, it is still that number when you multiply it using FFT. You just found it in a different way.
Oh, okay.
So you can still make an argument from that same expression for the polynomial coefficients, even though you used FFT to multiply your polynomials rather than doing that directly.
Wait, sorry. When you said BK minus I, were you referring to like the reversed polynomial or?
No, if you just have two polynomials, when you multiply them together,
Yeah.
the resultant coefficient on x to the k,
Oh, okay, okay.
AI times BK minus I.
Right. Yeah, that makes sense. Okay, so that's always, I guess, going to be true. That like that's where you would start, where it's like the AI BK minus I term.
Yes.
Okay, that makes sense. Thank you.
Other questions? We can probably stop the recording now unless somebody has a very relevant question that